Hello fellow P-Chemists, my name is Julia Liebel, and today I'll be giving a legacy talk for my P-Chem class of fall 2013. And today I'm going to be talking about tunneling and an analogy you can use to figure out what tunneling is going to look like in a potential energy curve that you haven't encountered before. But before we do that, let's pick up by doing a little bit of a preview, starting with what you've talked about in class, which would be the harmonic oscillator. And the harmonic oscillator has a potential energy curve that looks something like this. And as you know from class, its energy levels are spaced evenly. Now, tunneling is a quantum phenomenon that we observe in quantum systems, but not in classical systems. So if we're looking at the harmonic oscillator, a classical system, or a mass on a spring, would be pulled out this far to the potential energy curve. Then when you let it go, its energy would be converted from potential energy into kinetic energy here in the middle, and then back into potential energy over here. As it runs out of energy, it hits the curve and continues to oscillate between the lines of the potential energy curve. In other words, it doesn't go outside of the potential energy curve. So that's a classical system. But in a quantum system, you get something called tunneling, which is when the mass on the spring is able to penetrate into the forbidden region, which is this area outside of the curve. Now, it's important to note that this doesn't happen in a classical system, and it does happen in a quantum system, and here's why. In a quantum system, there's a certain amount of uncertainty between time and energy, much like there's uncertainty between position and momentum in quantum systems, as you've talked about before. What this allows is that the particle is able to borrow a little bit of energy for a small amount of time, and that amount of energy allows it to get outside of this potential energy curve and into the forbidden region. So if we draw our wave function, we'll see that it extends a small amount into the tunneling area. Now, the amount of tunneling is helpful when you're looking at a curve because it helps you figure out what the energy spacing is going to look like. So I'm going to give you an analogy called the bungee run analogy that will help you figure out the amount of tunneling that's occurring in a potential energy curve you haven't seen before. So let's start with a curve that has a different amount of steepness at different parts. In other words, something that looks a little like this, kind of flat, steeper, and then flat again. All right? So before we examine the tunneling in this curve, we're going to have to introduce the analogy. Now, I've linked below another YouTube video of a family playing on the bungee run machine, and it's a good visual if you're not familiar with the carnival game. Essentially what it is, it's the harness that you wear, and you're attached to a bungee hooked up to your back, and then you run as far as you can before the bungee snaps you back. And so there's a couple different factors there about how far you'll be able to get. One is the strength of the person who's attached to the bungee, and the other is how stiff the bungee is. If it's real stiff, you won't be able to stretch it very far before you get snapped back. But if it's more loose, you'll be able to run a farther distance before you get snapped back into the padding. So we can use this as an analogy for figuring out how much tunneling we're going to use by comparing tunneling, the amount of tunneling, to how far you can run with a bungee, and the bungee strength to the difference in energy between the energy level and the potential energy curve. Now in this case, we're going to be assuming that the person attached to the bungee is the same person every time, so their strength or speed won't make a difference. So if we look at this case, and we look at different energy levels, which I'm just going to throw on in an arbitrary spacing, we can examine the amount of tunneling that's happening at each level. So if we look at the amount of tunneling that's happening at this first energy level, which we'll call E1, the tunneling will be determined by the difference between this energy level here, this horizontal line, and the energy curve here, and how much it will have to borrow vertically between the energy level and the potential energy curve. So the amount of energy we'll have to borrow is V, or this curve, minus E, or the energy of this level. Now you can see here it's a pretty big difference, and that's going to make a difference for the amount of tunneling this is. If we've got a big difference in between here and here, that means that the bungee attached is going to be much stiffer, much stronger, And so the person won't be able to run as far as they would with a looser bungee. Consequently, this is a big difference. We think, okay, that's a stiff bungee, so the tunneling won't be able to get very far before it dies off. We're going to have a very small tail there. And then, if we look at E2, energy level 2, we see that there's a smaller difference in energy between the energy level and the potential energy curve. So here we've got a looser bungee than in the first case, and so the tunneling will be able to continue further before it dies out or gets snapped back. So we can draw a longer tail here. And finally, on the third level, we can see that there's quite a small difference now between energy level 3 and the potential energy curve. So up here, we'll see the largest amount of tunneling, and I'm just going to go ahead and draw these on this side so that I avoid my arrows. So here we've got a small amount of tunneling, a medium amount of tunneling, and quite a large amount of tunneling. Kind of like the three bears. All right, so then when we get up to this top level, as you can see, if we've got an energy level up here, there's not going to be really any difference between the potential energy and the level. So in this case, the tunneling will be infinite. It's as though there's no bungee attached to the person at all, because V minus E, this difference, is 0. In which case, the curve of the wave function will be able to spread out indefinitely, and the levels will collapse upon each other. Something else we can derive from this picture is that I've drawn the energy levels about equally spaced. But that's not actually what's occurring. What's occurring here is you've got a wave function with the most curve because it can't tunnel very far. Here we've got more tunneling, so there's less curviness. And then here we've got the least curviness. So the energy levels will actually get closer together as you continue up towards the flat part of the potential energy curve. Well, hopefully by now you're starting to get an idea of how this analogy works. Let's run through a couple more examples and the particle in a box model so that you can get an idea about how to apply this to other potential energy curves. So let's start with the particle in a box model, which you've talked about in class. However, you never mentioned tunneling when you were talking about particle in a box, and here's why. If we're looking at energy levels for particle in a box, we see that the difference between this energy level and the potential energy curve is infinity. You could keep drawing this line all the way up and you'd never hit the potential energy curve. So, since the difference is infinite, it's infinitely large, which means that the bungee attached to the person in our analogy would be infinitely strong. It'd be like a band of stainless steel. They wouldn't be able to run at all. They could make no progress, and what that means is that we see no tunneling with the particle in a box model. The wave function ends abruptly right at this potential energy curve because it can't borrow any energy to get outside of the potential energy curve. Now, if we modify the particle in a box model and have a potential energy curve that looks like this, we see that something a little different happens. Down here, the particle will have to borrow a significant amount of energy to tunnel, but it's not infinite. It's a finite amount, a large finite amount. So here we'll have minimal tunneling. But as we get closer to this potential energy flattening, that difference between V and E will continue to get smaller. So as we go up, there will be more and more tunneling that comes out until we finally get to this flattened part. Once V and E are equal, there will be an infinite amount of tunneling, and the levels will collapse upon each other. This would be a case where the bungee is non-existent, and the person can run forever, assuming that you're better at running than I am. So let's do one more example. It's called the Morse oscillator, and this is something you'll run into later in the semester when you talk about breaking a bond on a molecule. And the Morse oscillator's potential energy curve looks like this. It looks quite similar to the harmonic oscillator on this side, and quite dissimilar on this side. So as we look at the energy levels, which again I'm just drawing with an arbitrary spacing so we can examine the tunneling, we can look at a different amount of tunneling on each side here. Starting with this side, we see that the difference between the energy and the potential energy curve is about equal every time. these differences are roughly equal in magnitude, which means that the bungees are roughly equal in strength. Therefore, there will be a similar amount of small tunneling on each level when it's on this side of the curve. I'll just erase those so it's a little easier to see the tunneling. But on this side, it's a bit of a different story. Over here, we've got a decently large amount of difference between the energy level and the potential energy curve. But as you go up, this difference is going to get smaller and smaller as we start to reach the flattened portion of the curve. So on this side, we're going to see a small amount of tunneling near the bottom, but a larger amount of tunneling as we continue up. Until, as you might have guessed, when we hit this area, in which case tunneling will be able to continue forever along this side because there's no difference between V and E. So I hope this video has given you a chance to expand your tunneling knowledge, gives you another tool to think about tunneling, especially with a potential energy curve that you haven't encountered before. So just remember when you're looking at a potential energy curve to look at the difference between the energy level and where it intersects with the vertical potential energy curve. If this difference is large, that means you've got a large strength bungee, and the person isn't going to be able to run very far before they get snapped back. Likewise, there's not going to be much tunneling before it dies off. Now, if you have a small difference between your energy level and your potential energy curve, the strength of the bungee will be much less. It'll be a loose bungee, so the person will be able to run further before they get snapped back. Likewise, there will be more tunneling before it dies off. I hope this is a useful analogy for you, and thanks for watching.